You're about to listen to the Complete Developer Podcast, the podcast by coders, for coders, about all aspects of life as a developer.
I'm Will, the curmudgeonly experienced developer.
And I'm Beej, the optimistic newbie developer. Welcome to another episode of Complete Developer Podcast. This week, we'll be discussing how the efficiency of algorithms are measured. We'll first go over the different things people tend to mean when they say efficient, followed by discussing Big O notation. Finally, we'll discuss some practical examples of what you can expect from algorithms with different performance characteristics. But before we get started, Will, what have you been fighting this week?
Well, I am completely on Linux now, except for the desktop that I use for Agulous stuff, because I had to have Visual Studio and a bunch of those things. But the laptop's moved over, the servers moved over. The laptop was, I virtualized that operating system. It worked. Pretty happy about all that. It's, it's nice and stable now, finally. Comcast is really causing me a lot of problems here lately. I've clocked, I think, 14 or 15 hours on the phone with them in the last 3 weeks.
It cracks me up that you've counted the hours.
Yeah, I keep a timesheet on everything. But I mean, it's routinely an hour and a half to 2 hours to get things fixed. And it's not their tech support people, it's automated systems shutting stuff off, like going, "Oh, you don't have an internet connection because we say so." And they can't keep their stuff together. Or there's been problems with the set-top boxes upstairs for the TV. So like we were gonna, Kathleen and I were like, we were gonna watch X-Files the other night, and we couldn't because we couldn't get on demand, and I had to get up to like a level 3 tech support to get it. And I listened to their whole music. Well, let me just put it this way: I made 2 loaves of sourdough bread while I waited on their whole music, like from mixing the dough to it rising to baking it.
Wow.
Yeah. Like, now granted, I make it rise in the oven, at low temperature, but still, like, it's like 2.5, 3 hours of back and forth on the phone. And this is something I've come to expect as a feature of my life on a Comcast connection.
Yeah.
And Google Fiber is headed this way. If we can get them to quit colluding with, or if we can get Comcast and some of the others to quit colluding with local government to keep Google out of here, they're going to have some competition. And I'm not the only one of my neighbors that's ready to switch immediately. Like, one of the guys down the street actually said if it's less than $400 a month, he's switching. Like, because he's a tech guy too, and he's getting nailed constantly. He goes, I can look at my billing rate and I can look at how much of my time they're wasting, and that's a good financial decision.
I believe it.
So, yeah. In other news, it's also my birthday today.
Yeah, I had down for my first thing as happy birthday to you. All right, I'm not going to sing anymore, but
thank you for that.
Happy birthday to Will. We went out.
I'm mighty glad that didn't involve you jumping out of a cake.
Yeah. Now, if I did that, I'd be wearing a bow tie.
Yeah. There'd be like some stray beard hairs in the cake. That's just not good. So I saw you've been getting into the JavaScript a little bit, judging by the messages coming across.
Yeah, I've been doing a lot of front end work lately.
Speaking of hairs in the cake,
yeah. And I wrote some pretty nasty JavaScript towards the end of last week, and then today as well. A lot of nested loops and if statements. I'm just wondering, when can we get expression trees or something like LINQ for JavaScript?
Well, it's funny that you mentioned that. There's actually a project called link.js. That's LINQ. You can get it at linkjs.codeplex.com. It's a little bit older, but of course it's standard JavaScript, and JavaScript tends to be very backward compatible because of the web browsers don't really keep up. So if you could probably use that. There's quite a few other libraries as well that provide deferred execution, over lists or enumerable types.
Yeah.
That will simulate LINQ type things. There's also MapReduce type operations in jQuery and some of the other libraries. There's ways to do this and make it not horrendous.
Yeah, and it may just be that I'm not that experienced with JavaScript on this deeper level, especially with Angular, because been using quite a few like Angular for each loops.
There's another library called Breeze. Probably run into this with Angular stuff, but it's used for rich data. You can actually hook this into Angular apps and call back to the server and query through that way. That one is the URL for that one is getbreezenow.com. But yeah, Breeze is used for this kind of stuff, and I think I saw it hooked up to an OData data source. So like you can expose an OData endpoint and then query it.
Oh, neat.
From the browser.
Cool.
Obviously, you don't want a straight, piped through query, because that's how you end up with little Bobby tables. So yeah, there's ways around that, brother.
Let's go ahead and roll the music. This week for IoTs, I have a pretty interesting project. Make your own smartwatch from an old cell phone. I found this on tinkernut.com, and like all the best projects out there, this started out as someone trying to see if they could do it.
Yeah.
And a quote from the website, "The primary reason for this project is simply that I had an old cell phone laying around and wanted to find a creative way to repurpose it. It's a really well-written tutorial on how to take an old cell phone and turn it into a relatively smart watch. Looks like a fun weekend project for anyone interested in tinkering around with some old tech." I won't go through all the hardware involved, but the tutorial says it's about $43. But they did start with the cell phone, so I don't know how much an old like Nokia would be.
Yeah, there's no telling. I mean, I think most of us probably have one laying around if we could actually find it.
Yeah, exactly. So who's talking to us this week?
Well, we got a tweet from @StudyWebDev. Listening to my third episode of Complete Dev Pod today. Really great podcast for developers. And then they tagged it with, "My only complaint is that they cut their beards."
Thanks for the comment. We've chatted a bit on Twitter. The beards are coming back.
Yes, they are.
Of course, mine never left. I just trimmed it down. Will is growing his back out along with his hair.
Yep.
So
and that's because of the thing on the side of my neck that's, I can't really get that removed. Like it just kind of covers it up, plus the ugliness of my face in general. So,
what's funny is when his hair is cut really short and he's clean shaven, he almost looks like a little kid.
It's not as much of a problem now, but when I was like 25, actually up until I was 30, I was getting carded to go to rated R movies.
Mm-hmm.
And it wasn't like, the credit card, thing of, it was like, you don't look like you're old enough.
Yeah. I've never had that problem.
Yeah.
You've
had gray hair in your beard as long as I've known you.
I had gray hair when I was 18, and I had a full goatee when I was 16. So
yeah, I was going to say, I don't remember you ever not having facial hair. You may have, but I don't remember.
There's been a few times on and off, but for the most of my life, I have. So send us a DM on Twitter and we'll get you some Complete Developer swag. And guys, if you'd like some Complete Developer swag, leave us a review in iTunes or comment on the website or any of our social media. We post all of our episodes to Facebook, Twitter, Google+, for those 5 people, and LinkedIn. So starting the episode off, what is efficiency, really?
Yeah, so I wrote this outline, and it kind of took it was somewhat painful because this is a little bit hard. First of all, I want to throw out that efficiency is one of those weasel words that we talked about. We have an episode called Lessons from the Trickster that we published April 1st.
Mm-hmm.
And it's a weasel word is something that means whatever the person saying it means, not what it means. And that's what efficiency typically is when people are using that term. Usually they're describing how much effort is required to achieve a result. The term is quantified and used for comparison to something else's efficiency. Otherwise, it's not particularly useful. Like if there's one way to do something, it's, saying it's efficient or not is really not a value judgment because that's the only way to do it.
Well, You also have to think about like describing how much effort, but whose effort.
Yeah.
Because
if it's somebody else's effort, it's real efficient for me.
Well, no, that's not what I mean. I mean,
but that is what I mean. See, weasel words.
Yeah. No, okay. Let me finish what I'm saying, though. What I'm saying is your amount of effort to do something and my amount of effort to do something in C# is going to be different because you've been doing it longer. You've got a lot more experience than me. So what is efficient for me would be inefficient for you.
Right.
By that definition.
And I guess for the purposes of this episode, we're mainly talking about algorithmic efficiency, not work efficiency in trying to accomplish a task.
Yeah, I know. I wanted to point out that when you're describing it as how much effort that...
Yeah, how much effort for the computer. And by the way, that varies between computers as well.
Yeah, that's true. That's where I was going
Which
with
is
this.
why you do things like use your, you can use your video card to mine Bitcoins.
Yeah.
Because it can do some things really, really efficiently that you can't do with a CPU as efficiently. So that term varies. The biggest thing is being able to quantify it, and there's a lot of ways to do it. Most are fairly limited insofar as they describe how something scales. A lot of people will say, "Oh, this is efficient," or "This isn't." Well, it's like, how many items is this efficient over? Because without that description, it's not a mathematically based thing. It's an opinion at that point. And a lot of times people will say something's efficient and they really don't have any mathematical rigor. They just run it and it goes, yeah, it's not slow.
Yeah, talking about Bitcoin, I actually remember reading an article. This was probably a year or two ago.
They found some shortcuts.
Yeah.
Yeah. And what did that do? That dropped the value of Bitcoin.
Mm-hmm.
Because, hey, turns out if you can produce money more efficiently, the value of the money drops.
No.
Because it's like printing it.
Pretty much. Like what they found was it was more efficient to, rather than check yourself locally, to just send the bad with the good.
Yeah, and then batch check it.
Yes.
Yeah. And hey, it worked. Because they traded network bandwidth for CPU asynchronously. Because you really don't care how soon that comes back.
Exactly.
And that totally works. So I guess the next thing is to discuss why you should actually care about efficiency. And I'm going to start this off with frequently you don't. This is the real world, not academia. Academia loves going, oh, well, this algorithm is super duper efficient. And the real world goes, hey, I'm running this once. And after that, I don't care because it's a stupid batch script. It doesn't have to be efficient. It just has to work.
Premature optimization will really hurt your efficiency as a developer without providing a lot of real benefit to your application.
Yeah, we should do a commercial about how to cure premature optimization.
See, I was wanting to make that joke, but then
you let it go.
Yeah.
So it doesn't mean that you don't ever optimize, because obviously you do, but you need to pick the places where your effort isn't going to hurt your own efficiency versus the code's efficiency.
So basically, you need to be efficient when you're trying to be efficient.
Yeah. Preferably using recursion.
Of course.
Of course.
Typically, people tend to care about efficiency when the application is using too many scarce resources or when it's projected to do so.
Right. It's a fire extinguisher principle, right?
Yeah.
You care about fire extinguishers when the building's on fire, or when you think it might get on fire, or when somebody's looking who thinks it might get on fire. The rest of the time, it's a thing on the wall.
That's like, I've had some discussions in the past where we were talking about there are more efficient ways to do this, but it would take a rewrite of a major portion of the code base.
Yeah. And of Windows.
Yeah.
Yeah.
Yeah, but and we were discussing and going, all right, well, if the product owner wants that, if they complain about it or ask for it to be more efficient in this way, then we'll look at doing that.
Well, that's more efficient from a sales perspective.
Yes.
Because that's an algorithm too. These don't have to be all computational.
This is an example of being efficient when trying to be efficient.
Yeah.
It's yes, there are ways that we've learned that we could make this better, but that would require a lot of extra work, and we don't have time for that unless they say we have to do it.
Right. And usually what you're worrying about is how an algorithm will scale within a given range of inputs. So like if you're building your app to handle 1,000 concurrent users, the constraints that you're dealing with are not going to be the same for 1,000 concurrent users as they are for 1 million or for, a seventh of the planet's population. You get a whole billion. Like those, there's phase shifts based on scale that you have to do different things when it gets up to that level. Yeah, it's like searching a list, right? Like if you got to search a list with 1,000 items in it, the way you do that is very different than if it has 1 million or 1 billion. Because if it's got 1,000 items in it, you just load it all into memory. And if there's 1 billion, you really can't do that probably, and you have to deal with disk I/O and how that impacts things.
This reminds me of a conversation we had, it was a month or two ago, where I was talking about how I was loading the entire database into memory to find out where the problem in the code was, because we were in the dev database, so the dev data wasn't near as large as production. And so I was able to do that.
Yeah, well, and a lot of these people that talk about, I have big data, like if your data will fit in the typical RAM that's available on a server, it's not big data.
Yeah.
And a lot of those people go, I want to use these big data algorithms and, treat it like it's living on a sand somewhere. And it's like, well, you've got like 50 gigs of data. Cram more RAM sticks in there, load it into memory. Now you're more efficient. You're not big data. It's all about effort it's all about the amount of work you put in to get a result.
Exactly. So, moving along, big O notation.
Yes.
Now, this sounds familiar, but I'm drawing a blank.
This is the bane of a lot of people that start out in computer science, because the way that it is described is horrific.
Okay.
Like a lot of really difficult computer science concepts, the way it gets put is more difficult than the actual problem you're trying to solve.
That reminds me of when we were talking about design patterns.
Yeah, it's exactly that sort of thing. But it's design patterns for people that like Greek letters and weird symbols.
So me.
Yeah. It's pretty horrific. But basically what you're doing with this notation is it's a way of expressing the growth rate of the worst case of performance for an algorithm. Not the best case, the worst.
Sounds scientific.
Yeah, because it's like, how bad can this get?
Yeah.
Because that's what you really need to know.
And that's the one that usually gets you in trouble. Like when it's working at its best, no one notices. When it's at its worst, customers are calling in. Yeah.
Or you have a cascading failure and customers can't call in, which is even better. It's especially great, because things will not get exposed except, during Black Friday sales. Mm-hmm. Something when, hey, the company makes most of its revenue for the year on this day. That's when things are scaling to the point where stuff actually blows up. Mm-hmm. And most people don't do enough load testing to really avoid this very well.
Yeah.
So that's when you get hurt by it.
So it's also important to note here that Big O is a model for the worst case scenario under certain constraints.
Yes. And I like to throw this out because they never do in computer science class. And I have watched, fresh-faced, happy computer science graduates go, oh, this thing scales linearly. There's not a problem, until they have a disk read error on a server somewhere, until there's, a bad hard drive or something like that. And then, well, why is my algorithm blowing up? It's like, well, because the way you were taught about it wasn't quite what we deal with in the real world. It's close.
And the first of these is normal system operation.
Yeah. And I guess, I hate to paraphrase Johnny Depp from Pirates of the Caribbean, but, the Big O notation is kind of like guidelines. It's like the pirate code. That wasn't Johnny Depp. That was the other guy.
That's how a lot of people view the speed limit.
Yeah.
It's a suggestion.
Yeah. So, like, if your hard drive's starting to get bad sectors or Comcast is performing like crap, not that we know anybody with that problem. Yeah.
Sorry, I just read your notes.
Yeah.
If Comcast is performing like AOL from the mid-90s.
Yeah. Which was this week. Actually, I mean, seriously, 400 millisecond ping times for Google.
Holy cow.
Yeah, with like 75% packet loss past the firewall. And that was after the first call. So you can understand why I'm a little cranky with them. Big O notation does not handle this problem.
Mm-hmm.
Well, it does if you're like talking about optimizing the network card and the things that go wrong there. But like if it's sitting on top of that, that's not really in the bailiwick of constraints that you worry about.
Yeah,
for this particular thing.
It's not your algorithm.
Right.
It's what your algorithm
something
is.
Else.
Yeah.
It's just, you kind of cut down the set of things that could be wrong to the things that you can control. The next thing to remember here is that the growth rate is described as a mathematical equation.
It should be understood that this equation is within a range and is not necessarily absolute to extremely large values. For instance, a hash table that has a constant lookup time may not be performant on extremely large data sets due to things like paging memory to disk or hash collisions. What's a hash collision?
That is where you get two values that have the same hash. So when you look it up, you've got to have a way that basically resolves it. Goes, hey, this isn't the right thing because something else is already sitting here.
Yeah.
So when you're inserting, you have to go, okay, well, I'm going to jump to this next position. And if you keep hitting those, like the hash set is full, you're going to jump around for a while, if that makes sense. So, this is not particularly describing that. It's describing, what happens when it's fairly sparse.
I kind of follow you.
Yeah. The other thing is, as the data set gets smaller, this also becomes a problem because think about this. We're talking about the growth rate of an algorithm, right? But there's also, it's sort of like fixed costs and variable costs in a business. There's a fixed cost for I have a location, I have rent, I have this, I have that. And then there's variable costs. It's how many widgets do I have to buy to produce this many, I don't know what, sprockets. Say sprockets. That's variable cost. But the fixed cost is the building. Well, as you produce fewer sprockets, the proportion of the cost that is the fixed cost goes up.
Yeah, that makes sense because it's fixed. But as you have it's the proportion that changes, not
right.
the cost, but the proportion of your income that goes to it.
Right. So if you scale down in the number of items that you're dealing with, using a very highly efficient algorithm for lookups may not be of value because of the amount of time spent spinning the thing up.
Okay, I have a great way of putting this in different terms. Okay. All right. So you have rent. Rent is the same. Throughout the year, it may go up, but throughout the year, rent is the same. Your hours get cut at work. The amount of your paycheck that goes to rent goes up, but your rent did not change.
It's the difference between two curves.
Yes. Calculus. Woo!
Yeah. It's kind of tricky also to predict algorithm growth rates on modern systems, especially with what you and I work with, except for the one thing I work with, because they're managed memory. So JavaScript is, C# is, Java is. A lot of modern languages, they manage the heap.
Yeah.
So when you allocate an object, like you don't have to say, hey, I'm done with this, throw it away, except when you do. Which is great.
Yeah.
That's a whole other can of worms. But
we'll talk about that some other time.
Yeah, the fact that the thing deletes it for you also means that you can't predict how much you're going to hurt things. So, like if you don't allocate memory in a correct fashion on the .NET platform, you could actually not be really using a whole lot of memory transient, but you could be over allocating and you could cause a heap reallocation and kill your performance.
That strangely makes sense. I was thinking about when I asked you about garbage collection, and you said if you ever saw garbage collector in my code, you'd kick me.
Yeah, if you do gc.collect in your code, yeah, it's an instant ball shot. I'm just telling you.
Yeah.
Like that's on principle.
Yeah.
That's not okay. Bad things happen to bad people when they do that. So towards that end, we're going to try to express this stuff in a way that actually makes sense versus the way I was taught in school, because that hurts and it's really not good for audio.
Yeah, you didn't have me in class. I had a reputation when I was in grad school for comparing everything that we were taught to a movie.
Yeah.
Of course, I was in grad school for clinical psychology, so...
And he was in clinical psychology for a reason. But, yeah, so I'm going to try to lay this out mostly with one point that didn't quite work out in terms of searching a list of people based on their name and other attributes, because it's probably the easiest. But the idea here is that you understand these concepts and that you're able to apply them in other situations more than it is to go, oh, well, this is, this algorithm efficiency because nobody cares. Like your code's either faster and better or it isn't. Like it's nice to be able to quantify it, but at the end of the day, be able to do something with it. We're going to pick on a random unnamed local music star for this one. Actually, it's not unnamed. We're just going to go ahead and say it. We're going to pick on Taylor Swift because I've got an 8-year-old who absolutely loves her stuff.
All right. Well, I want to take a moment to talk about the time that we met Taylor Swift. Before we get into using her as an example, which is the other reason, because she was a total sweetheart. She was super friendly. This was right before I went off to med school. Will and a couple of my other friends took me out to dinner to
send you off, basically.
Yeah, it was a really, really fancy steakhouse that we all went to. So we're sitting there, and across the table from us.
Yeah, she was behind me.
Yeah, behind you, because you were sitting across from me.
Yeah.
No, she wasn't. You were sitting beside me. So I look up, and this group of people a little bit younger than us comes in, and this one, which
is like everybody in Nashville.
Yeah, this one, I'm like, she looks familiar. Why does she look familiar? I leaned over to Will, and I'm like, is that Taylor Swift? And he's like, how should I know? I'm like, your daughter absolutely adores her. He's like, if she starts singing, I can tell you.
Yeah.
So I look her up on my phone and I show him a picture. And he's like, I think it is. And I guess she saw us.
Trying to figure it out.
Yeah. And for those of you that aren't in Nashville, Nashville is known for just leaving celebrities alone.
Yeah.
But she gave us this look like, please, I'm out with my friends, don't. And so we didn't. We
didn't bother.
We didn't bother her at all. And as we were leaving, I walked by their table just because it was on the way out the door. And she leaned over and said, thank you. And I was just like...
Well, and I ran into Steven Tyler, and I felt sorry for him because he couldn't pick out sheets for his bed without 15 people coming up.
Really?
Yeah. And I was thinking, maybe I ought to go over there and go, do you need somebody scary looking to just stand there and frown at people? Because I could do that. Because, my wife is picking out sheets. It's like, I don't have anything to do.
It must have been a lot of new transfers.
Well, he was
new arrivals to Nashville.
He was also dressed to draw attention. He was doing the Steven Tyler thing.
A mutual friend of ours saw him at the movie theater, and nobody was coming up and talking to him. And she said he looked like he was sad that nobody was.
Yeah.
So I don't know.
But anyway, so we're going to pick on Taylor Swift for this one because we need something that makes this stick so that it's not as difficult as computer science people make it. Yeah. And that seems to work okay. And the reason for that story, understand that we think the world of Taylor Swift, even though her music isn't exactly to our tastes. Yeah, I tend to like more of the Cookie Monster metal.
I had to explain that at work the other day.
Yeah. But, we're using her as an example because everybody knows the pop culture around it. And so hopefully this will help it stick in your mind. The other thing we're going to try to do is we're going to try to do this without referring to calculus.
Which makes me very sad because y'all know how much I love math.
Right. But it also keeps me from tripping over my own feet.
Yeah.
Because the whole, auditory, trying to speak that out and get it right, that's not going to happen. So, but that said, if you've got calculus in your background, you may catch on to a few of these things quicker than a lot of folks. Think about derivatives and you'll be fine. Like how those are calculated, because this is what, the rate of change is effectively what's going on, or the rate of acceleration.
Yeah. Tangent to curve. Gotcha.
So that said, let's get into it. Different types of growth rates as expressed in the big O notation. The first one is O of 1. That's O with parentheses around a 1. That's called constant time. Growth rates expressed in this fashion are exactly the same regardless of how large a data set is. Again, within constraints.
This is what you get when you access an array item by index.
Yeah. It's basically saying, hey, here's the pointer to the start of the array. Here's how many units to jump, and the units of known size. Then give me the item there.
It's like when you're writing mid-tier, it's like a get by ID.
Yeah. Well, that's a little interesting too when you get into the database side.
Well, yeah, I'm talking the mid-tier. It's
again, it's like the thing about the whole garbage collection. Like, this is good to understand from a high level, but like if you actually go, okay, let me examine exactly what these guys are saying, you're going to get into the weeds real fast. Another way to think about this, for our example, if Taylor Swift is throwing a party at her house and has a list of Hollywood A celebrities and needs their addresses to the invitations, and she's a complete nerd, she might calculate a number based on their name that tells her precisely where they are in her address book. In other words, it's not any more expensive, no matter how many people she knows, to calculate that number and go to that place in the book.
Searching by index.
Yeah, it's an index-based search. Now, you'll note that a normal human being doesn't do this. In fact,
must not be normal.
You're not going to see that in a depiction of Rain Man, even. Right? The reason is computers are a little better at math than we are. That's their native tongue, whereas we just kind of glued it onto ours. This isn't something you're going to see in real life, but it's as if that was the case. This is where things like hash tables come in.
Okay,
it's calculate a value, and it's this item in the index based on this other thing. That's a very simplistic way of explaining how you index things. I know there's more to it than that, but just avoiding, the angry Twitter comments about, you're wrong about this. Like, I'm not getting into the depth and complexity on purpose because it's not
the purpose of this episode.
Right.
Gotcha.
So that's constant time.
Next is linear time, or O of N.
Yeah. That's an O with an N in parentheses. And that is the idea that the worst case for accessing an element, in a list is directly related to how many elements are in the list. In other words, you're going through all of them, potentially at worst, to get the one you want.
I follow you.
Right. So it would be, again, going back to the the Taylor Swift thing, it would be as if she opened her address book to find somebody and looks them up by flipping through every single page.
So like a non-alphabetized address book where it's just, as she got the address, she wrote it down next. And which
like
I've had.
The way I organize my work notebook.
Yeah.
Which is atrocious. But yeah, like in other words, the rate of growth is that if I have N items, I have to look at up to N items to find.
Okay. So the worst case scenario is it is the last item in the list, and she has to look at every single one to get to that.
Yes.
Gotcha.
And obviously, people typically don't do this for the most part, but you and I both know very disorganized people, and we've been disorganized people. Like, this is the hallmark of a disorganized person, is a inefficient algorithm for doing things.
Yeah. And, I mean, most of your address books even come alphabetized so that you don't do that.
Yes.
Yeah. Or people may, even if they're just putting them in as they get them, you can at least go, all right, I know I met this person and got their phone number, 2 months ago, so I can flip back to about 2 months.
Yeah.
And,
Well, that's even not that bad. It's like, I knew them, I met them at some point, and I don't know.
I know, that's what I'm saying. I'm saying, like, people in general don't do this because...
Yeah, we tend to arrive at computing algorithms organically because the alternative sucks.
Mm-hmm. Hey, guys, I just want to interrupt here real quick to tell y'all about a brand new conference that I'm going to be attending this coming April on the 21st and 22nd called Codeland. It's put on by our friends over at Code Newbies, and you can check out more about it at codelandconf.com.
O of N is what happens when you can't quite optimize something or it's not worth optimizing.
Yeah.
So think of, the growth rate between, I don't know, say, I hate to pick on Nickelback, but not really that much. If I have a list of Nickelback fans versus I have a metropolitan phone book and I want to search through it linearly, like that growth rate is horrendous. That goes from 10 to 1 million.
Oh, wow. Nickelback has twice as many fans as we have Google Plus followers.
Hey, And there's somebody out there just clenching their fist right now around their steering wheel. Just relax, bro. We're just picking.
Yeah, I mean, realistically, if Nickelback didn't have fans,
they wouldn't be in business. Yeah.
Yeah, we wouldn't be making fun of them.
Yeah. So that's linear time. That's the understanding there. The next one is O(n) squared. And this is where the growth rate expressed here scales to the square of the number of items in a list. And we got to torture our example a bit here, but we can bring in some pop culture anyway. Let's say that your person list is a list of Hollywood celebrities, and that celebrities are identified by name and by an ID number, and that each record has a set of child records that tells you which other actors have talked smack about them and when.
Okay, so you have a set of celebrities. Within that set, you have a set of all the people who talk smack about them.
Well, for each one, they've got a
like I said, within each celebrity in that set of celebrities. So you have a group, you have a list of celebrities, and each celebrity has attached to it the list of people who have talked smack about them.
And you can't get to it from outside there, right? It's not in another table. It's nicely indexable. You got to get to it from that aggregate root.
Okay.
So let's say that you've got that. The inside list only specifies the ID of the person talking smack, not their name. And you want to get a list of the names of everybody that's talked smack about everybody. But let's take the example of Taylor Swift, right? Well, what do we have to do? We have to do an O(n) lookup to find Taylor Swift in the list first.
Mm-hmm.
Then we have to go down to the records that are under her and find, okay, here's Kanye West, here's Katy Perry, here's all these things. But we don't have the name, we have the ID, so we have to do another O(n) lookup on the master list. So if we're going to get it for everybody that's talked smack about everybody, it's an O(n) times O(n), so it's O(n) squared.
Okay,
Does that make sense? It's a loop within a loop, effectively.
So did you write this episode because of some of the stuff that I asked you about this past week?
I think that was part of the genesis of it, yeah.
Yeah, because I've had to deal with some of this to where all I had was the ID, and then I had to go look up. And
the other thing is I wrote it as a matter of efficiency because there was another episode that has been rather painful and I'm still working on, and I realized I wasn't going to have it done in time and be able to enjoy my Sunday evening. So I did this. And I still didn't get this done.
I just find it hilarious because I'm like, you're talking about this. I'm like, I've been dealing with this.
Yeah.
Something very, very similar to this the last 2 weeks, and I've got another 2 to 3 weeks of this exact same problem.
But you understand what this kind of thing would be, right?
Yeah, I do.
And you might have O(n) cubed.
Yeah.
Where now she's trying to find her allies that have talked smack about the people that are talking smack about her. And then you have the 6 degrees of Kevin Bacon, which is going to be O of n to the 6th.
Okay.
But you can optimize some of that away, where it's not a looping thing. But anyway, we won't get into that because I did while researching this, and it's fascinating, but we're not going there. So does that kind of make sense?
Yeah, I'm following you here.
So
next you have exponential, which is O of 2 to the n.
And this is what you pretty much call just an absolutely insane growth rate as far as algorithm efficiency. You really have to have a small data set to be able to get away with this without getting burned very, very fast because it's an exponential growth rate. I can think of a social situation actually involving this person, but it's something that hits the tabloids and it's not nice, and I really don't think it's deserved. So we're going to go full on Aussie and we're going to talk about drop bears. Are you familiar with drop bears?
No.
This is something that Australians tell you about that's a joke. It's not a real thing, but it's basically like an evil panda, or not an evil panda, an evil koala bear that drops down and bites people in the head and they die. Okay? So to describe this sort of algorithm, let's say that you're tagging drop bears in Australia. And this is bad. I don't like this sample. This is something we avoid, but we'll go with it. Each pair of 2 drop bears will have a total of 4 offspring, after which they immediately attack people and are euthanized by the authorities. This is a math word problem, right?
Joy.
You want to start tagging the descendants of these drop bears for science, right? And you're going to wait in generations. How many drop bears at most do you have to tag? Let's say they're mutant drop bears, whatever. What does that do? Well, it grows every generation. If there's 2 drop bears and they have a total of 4 offspring and none of the offspring die until they've produced offspring, what's the worst case scenario for how many you've got to tag? Yeah. It's that sort of thing. So if you see this, think of evil drop bears jumping down and biting people on the head. You don't want to see this.
Run.
Yeah.
Run screaming.
Yeah. And, you just really want to reiterate, like, this sort of setup is kind of hard to achieve unless you're doing really, really naive things with your data.
Yeah. So to quote Doctor Who, basically, run.
Yeah. It's just a little bit worth saying that way. But you will see this, and if you hear somebody go, oh, this is, O of 2 to the nth, or O of X to the whatever power, or X to the N power, or X to the N to the whatever power. I've seen that a couple times too. That's not a good place. That's not happy. Okay, that means that if every item you add to the list makes it, orders of magnitude worse in terms of, CPU utilization, hard drive space, whatever, your metric happens to be. Okay.
So next you have logarithmic time. And are we talking log base 10?
It depends on the algorithm. And the one I typically use to explain this to people is binary search, which is going to be log base 2.
Yeah. Okay. So it would be O of log of n.
Right.
So log base 2 of n.
Yeah. And, if you want to get into the math of logarithms, that's great. They're handy. It'll save you time. Learn the math. I'm not teaching it to you. However, let's talk about another situation. So enough about critters getting maligned as part of a running gag. Let's talk about Taylor Swift.
I like talking about Taylor Swift.
Speaking of, man, she does catch the crap sometimes.
She does, but you know what? Like I said,
yeah, decent human being. But let's assume that for a moment she decides to be evil Taylor Swift. And she decides that she's going to get even with the people that are trash talked her.
Okay, so I watch way too many bad sci-fi movies, and I just had this mental image of Taylor Swift with a goatee.
There you go. Yeah, think of Taylor Swift with a goatee, and yeah. So she's going to get even with all the people that trash talked her, right?
All right.
So she decides she's going to send them invitations to a party at Kanye West's house and not telling him they're coming, so he looks like a total jerk. Not that that's abnormal.
True. Right? I have no complaints there. Yeah, I'm not going to argue that.
I like his style, but man, sometimes you're like, man, what are you doing? But this time, to be efficient, when she looks up addresses in her address book, she starts in the middle of the book and she goes further back if the name is before that point, and goes forward if it's after that point.
So she does a bubble search.
Yeah. Well, she splits the list and then she splits it again.
Yeah.
In other words, she's
bubble sort.
Well, that's a binary search.
Yeah.
Yeah. Bubble sort is that same kind of thing, but you're actually sorting.
Yeah. Yeah. That's true.
But let's say that she approaches it that way, right? That again is called a binary search. That is up to O of log n, log base 2 of n. And the reason for that is that while the search time scales with the number of items in the list, it doesn't scale linearly.
No.
Because she has to greatly increase it to increase it a little bit on the search time, because you're having the list every time. So that's what people mean when they're saying that, is I'm basically subdividing a list. In other words, I'm honing in on it and I'm not running it linear.
So this is a good thing, then.
Yes, it's an improvement.
Okay, so the time goes down,
provided that you have a big enough data set for it to matter.
That's true.
Otherwise, you lose. You may spend more time going, okay, what's the middle between these 2 points? Let me jump there, versus just blowing through the whole list.
That's very true.
So yeah, understand that this is one of those comp sci things that the answer is kind of like what does grandma need from the drugstore? Depends.
You listened to that episode too.
I did.
For those of you that don't,
I about ran off the road.
I wasn't expecting that. Thankfully, I was sitting in traffic when that. But that's from
.NET
Rocks.
Yeah. And I forget which episode it was, because I've binge listened here lately. Okay, this is how that we typically talk about scaling factors with algorithms, like how much extra work it is when you add elements to a list or add it to a data set or do a certain number of operations or calculate certain things. You'll see this with disk I/O. You'll see it with memory utilization, CPU, network I/O. Like if I have a couple of people, like in a multiplayer video game, right? If I have two people and they have to communicate the whole time, there's network traffic. If I have three and my algorithm is such that all three have to communicate, I've increased the network traffic more than a linear increase in the number of nodes. And so you'll see this sort of thing reflected in a lot of places. So let's talk about how we're going to actually use this in real life.
To be honest, you're going to run into this in interviews more than actual development.
Yeah, at least as far as the direct use of the terms and the way of notating it. That's an interview-only question. The rest of the time you go, hey, this takes less work. And okay, that's how the conversation goes. It's not, oh, well, this is O of n squared and this is bad, okay?
Yeah.
Like, that's not something that comes up unless it's really, unless the opinion is very, very split and you have to get out like the alpha nerd to figure this out. Like, that's not something that comes up very much. I can think of like maybe twice in my career that this has actually happened, but you do have to understand the concepts.
Yeah, I would say that being said, being able to characterize how something uses more memory, more CPU storage, or network bandwidth as the application scales is critical.
Yeah.
And having some mathematical understanding around it is going to help keep you from just guessing. And you should also be very cautious in regards to optimizing at the wrong time.
Yeah. Like when you have two users, your optimization probably should tend towards fixing bugs and onboarding more users so that you have a paycheck.
Unless, of course, you're writing an app that you're only going to have two users.
Yeah. And if you got, some, multi-billionaire that's funding it, okay, whatever.
Or a state government.
Yeah. Or a state government. But, again, that's not a typical situation. Yeah. Like, be efficient when making things more efficient. Mm-hmm. Again, optimizing at the wrong time can actually hurt performance. So it's important to kind of bear that in mind and be careful about it. Another thing, as you get into bigger systems, when you deal with situations where you got load balancing and you got multiple nodes and microservice architectures and distributed system programming type things, or just large, huge amounts of data, it's important to remember that this notation of scaling can fall flat on its face at larger scales, especially when system constraints are reached. You'll see things like, oh, hey, all of a sudden now it's paging to disk and my I/O just got cut in speed by like 98% because I'm using too much RAM because of the way I'm trying to do it. There are essentially phase changes in the way things work that necessitate going back and fixing your algorithm for a higher load. So it's stuff that wasn't an advantage. It's at a small scale, at a large scale, it's the only way to make it work.
That makes sense.
And so that's why I wanted to point out that, hey, they say in school, they're like, oh, this is O of n or O of whatever. Well, it's O of n up to a point, and then it's, there's other operations that take place, and now it's O of 2 to the n to the n.
Oh, wow.
Or something, just absolutely horrendous because, oh, by the way, Cat 6 can't carry all the packets anymore.
It's like, remember that theoretical physics is beautiful. And actual physics includes equipment failure and bad measurements.
Yeah. And a trebuchet falling on your face.
Yes.
If you do it wrong, it's like, oh, this is perfectly within constraints. And it turns out that a hair fell on the payload and now the thing breaks.
Yeah.
Yeah. So, use these as guidelines.
That pretty much wraps us up. Before we close everything out, Will, what do you have for us this week for Tricks of the Trade?
We talk about mathematical rigor. Just a little bit. Just a little miniature rant.
I like math.
I hate numbers and stuff. There's like too many of them. Let's talk about mathematical rigor in computer science. I frequently see people test things out and they'll go, okay, I'm going to test this for 1,000 iterations or test it for 10,000. Some large number that is very obviously base 10, very obviously chosen based simply on just being a large number. And I think that's a little bit risky because it tends to indicate a lack of analysis. In other words, do I have a cohort that's large enough to test this over? Have I thought about the segmentation of said cohort? Have I thought about what the actual load is versus here's a random round number that I'm going to throw at it? And so I would encourage you to take a little bit of time and actually get a statistics book and look at this and try to figure out what numbers you actually need to have a confidence interval that makes sense versus just throwing out a random round number that sounds good. And it's more for avoiding the situation where you say you tested it and then you push it into production and it blows up because you didn't test with enough rigor. So just throwing that out there as something to kind of think about as you're doing a little bit more advanced stuff. I know this is not something that junior and mid-level developers deal with a lot. It's more of a system architect type thing, but it will bite you if you're not careful about it. So that's all I got.
Stand by for Titanfall.
If you have a question or comment for us, please email us at neckbeards@completedeveloperpodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed under Creative Commons. The intro music for IoTs is Hillbilly Hip Hop by Jason Belcher. For references, show notes, and to sign up to our email list, be sure and check out the website at CompleteDeveloperPodcast.com. You can also follow us on Twitter at CompleteDevPod and like our page on Facebook to keep up with the news about the show. Thanks for listening. See you next time.